Hi everyone, good morning. Welcome to the Euroviz session on
Hi everyone, good morning. Welcome to the
interaction.
Euroviz session on good morning. Welcome to the
It's morning out here in the West, and I'm Jason Dykes from the GI Centre at City University of London, which is just on this little bit of rock that's moving out into the Atlantic away from Europe. And all of my colleagues here are going to be giving their talks. They're way out in this direction in North America, so they're just having their breakfasts. But it means they're sharp and ready to answer your excellent questions. Yeah, so we've got 4 authors, 4 nice talks, and I'm not really going to say anything else other than if you want to appear on the map at the end of the session, you know where to look. You add your coordinates just down here. Okay, without further ado, I'd like to introduce John Thompson. John and his colleagues from Georgia Tech have a paper on authoring animated graphics and the design space for animated transitions. So, John, over to you.
Thank you for tuning into my talk on animated data graphics. My name is John Thompson, and I'm a PhD student at Georgia Tech. This is work I completed with my collaborators at Adobe Research, Leo Liu and Will Lee, and my advisor, John Stasko. Our theory paper contributes 2 things: a survey of the design space and a study with designers. The design space provides a framework that describes animated data graphics, while the study reveals how designers think about authoring such animations. We intend these contributions to inform the design of future authoring tools for designers. Animated data graphics refer to a type of animation for graphical objects that in part represent underlying data. Starting with a data graphic at rest, animation is driven by changes or updates to the data graphic's properties. These changes can be data-driven. Other changes are driven by the visuals alone, serving a presentation role. Let's start with some examples focusing on animations that are data-driven. In some cases, the data mappings are altered. Here are the X position changes from a nominal to numerical scale. Animations may also be driven by updates to the underlying data values, such as this visualization transitioning the data from Los Angeles to San Francisco counties. Next, we'll look at animations driven by visuals alone, serving a role in presentation. Animation annotations can emphasize content of importance, such as highlighting a specific year, or visual changes to the entire viewport of the data graphic, such as this initial rotation of the chart that cues a transition to a histogram. Animations benefit by combining data-driven and presentation changes. Here, the underlying data representation changes from many lines to one average line. At the same time, the stroke color of the line and annotations visually cues the viewer to this change. Currently, many designers opt for the expressivity and flexibility of programming tools and libraries to create such animated data graphics. However, programming incurs a steep learning curve and demands significant cognitive effort, while requiring programmatic thinking to extrapolate textual code into animations. On the other hand, interactive authoring systems such as Flourish and Data Clips provides an approachable visual interface to design animations without programming. However, these tools only support a limited number of visualization types, and lack support for pacing and animation effects design. The motivation of our research is to inform the design of better authoring tools that are approachable for designers with little or no programming experience. Our approach is twofold. First, we need to understand what are the building blocks for animated data graphics. To that end, we contribute a design space. Based on a survey of examples, we derived primitives as building blocks for archetype compositions. The design space acts as a framework for future authoring tools. Next, we investigated how designers conceptually approach authoring such animations. We conducted an ideation study with 14 designers. We synthesized the discussions, ideas, and sketches from designers as authoring preferences and guidelines for future tools. In the first half of this talk, I will cover our design space. We first considered describing the design space with pre-existing animation taxonomies such as Robertson-Harrer's taxonomy or Fisher's list of animation types. Later, Amini et al. Based the data clip system on visualization and animation type tuples. To realize a broader spectrum of animation designs, we seek to define animations as building blocks rather than by taxonomy. Most similar to this approach, Chalby's thesis differentiates between data and visual changes at the component level. In search of these animation building blocks, we surveyed 52 examples selected from award showcases, media outlets, and freelance designers. The examples include data narrative articles, data videos, visualization slideshows, and interactive maps. During weekly meetings over 3 months, we defined compositional primitives that were generalizable across datasets and visualization forms. The output from our survey were primitives and compositions that characterized the design space. The primitives are from the object, graphic, data, and timing dimensions. To validate these primitives as building blocks, we propose compositions, 10 transition types composed by the object, graphic, and data dimensions, while 4 pacing techniques are composed by timing primitives. Here, we quickly summarize the primitives of our design space. The object dimension refers to what type of graphic object, delineated by role, transitions during the animation. The graphic dimension describes how an object changes visually from one state to the next. The data dimension describes how the underlying data and its representation changes. Finally, timing describes the order and pace at which objects' properties move from start to end of an animation. Next, we'll recognize a set of 10 transition types based on the primitives from the object, graphic, and data dimensions. Transition types are differentiated by which primitives drive change between start and end of an animation. Let's start with an example from the Visual Introduction to Machine Learning project. Here, rectangles represent a home with attributes such as price per square foot, number of bedrooms, or even elevation. Elevation is along the y-axis here. This project demonstrates how machine learning classifies the homes based on if they're in San Francisco or New York City. This chart shows that elevation may be a good way to distinguish between the two cities. We transition from this chart by modifying the rectangles into circles. This is an example of a visual alteration. We define the transition type based on which primitive drives the change. We break the animation down further from start to end frame. The rectangle glyphs are the only objects that animate, but their numbers and data do not change. However, the glyph's shape type and width visual attributes are altered. Visual attributes drive the animation change here, which is why this is a visual alteration transition type. Here's another example that completes the stage transition into a scatter plot. The x-axis is now representative of price per square foot. This is an example of a data encoding alteration. Again, we break down the animation from start to end. The glyphs, now circles, are the only objects that animate. However, this time visual change is driven by data. In this case, the data encoding for X position is altered from a nominal scale to a numerical scale. Data encodings drive the animation change in this case. Hence, this is a data encoding alteration. Our design space describes 10 transition types. Similar to our examples, they are defined by which primitives drive the animation change. For more details on all 10 transition types, please refer to our paper. Our design space also includes pacing techniques composed by timing primitives. We include staging, layering, staggering, and looping as compositions of timing. Pacing techniques assist the audience to perceive and apprehend animated transitions. For more information on pacing techniques, again, please refer to our paper. We envision future authoring tools should prioritize these compositions and build upon our primitives as a framework. In the second half of this talk, we cover our ideation study with designers. We investigated how designers conceptually approach authoring such animations. We first reflected on graphic animation tools, such as motion graphic tools and user interface prototyping tools, or sketch interaction tools for illustrations, as well as familiar presentation tools. Instead of focusing on specific interfaces or interactions, we identified 3 prevalent authoring paradigms for graphic animation: keyframe animation, procedural animation, and presets and templates. With keyframe animation, designers specify properties of graphical objects at certain points in time as a keyframe. The graphical user interface for keyframing is usually a timeline. However, prototyping tools implicitly treat scenes as a keyframe. Procedural animation is popular for animations involving many objects. Animation is created procedurally. Starting with an initial condition, an engine generates motion by adjusting a set of parameters. User interfaces for procedural animation include programming languages, traditional web interfaces, or even sketching. With reusable presets and templates, users simply choose from a list of available animations to apply. Presets and templates lower the learning threshold, but lack design control. To understand designers' preferences for these three paradigms, we conducted an ideation study. 14 designers with experience in graphic, visualization, and animation design participated. Sessions lasted at most 90 minutes. Participants watched an informational video that explains all three authoring paradigms first. The participants then completed 6 ideation tasks, and finally, an informal interview. We selected 12 animations from our survey of tasks. Each participant experienced a condition of 6 animations from 2 example projects. For each task, we prompted participants to talk about how they would conceptually approach authoring the animation in an ideal authoring suite. The results were audio recordings and sketches from these ideation tasks. We transcribed recordings and coded them based on the authoring paradigm expressed by the participant. Overall, participants described authoring with keyframe animation most frequently. This could be due to participants' reported familiarity with keyframing tools. In line with our overall results, designers had a preference for keyframes for the majority of transition types. At the primitive level, participants envisioned specifying keyframes on glyphs or groups. Participants expressed concern with scaling the keyframe approach. Future authoring tools should support auto transitions and batch alterations. Designers preferred presets and templates for simple animations such as appear and disappear. Paradoxically, designers also prefer templates for complex, yet often used transitions such as highlighting, filtering, and data ticker. Furthermore, designers prefer templates to reuse delay-based pacing effects such as staging. Designers prefer to describe complex animations such as simulated processes with the procedural paradigm. At the primitive level, participants desired to procedurally create delay-based functions such as staggering or to manipulate data presence and data transforms. Finally, we found evidence that an authoring tool should combine these three paradigms. Participants provided design ideas for multimodal interfaces such as a storyboard and timeline tightly coupled to easily navigate between paradigms. Our results detail the paradigm designers prefer for tasks and primitives, which is crucial for balancing these paradigms in one tool. In summary, our theory paper contributes a survey of the design space and authoring preferences and design guidelines from a study with designers. Our next steps are to design and implement an authoring tool based on the results from this work. Thank you for tuning to my talk. For all the details and materials, please consult our project page or paper, or contact me directly.
Okay, thanks, John. Nice work. So I'm hoping we'll get people asking questions on YouTube and in Discord.
Okay, thanks, John. Nice work. So I'm hoping we'll get people asking questions on YouTube and in Discord.
And we do have a question from Aspen, who's asking if you could explain your decision to focus on the building block approach rather than the taxonomy approach. And where was the evidence for that in the authoring paradigms?
Yeah, so we decided to focus on these building blocks or primitives as a way to inform future authoring tools instead of using taxonomies, because taxonomies basically only allow designers to pick a single types of animations, whereas a framework of building blocks would allow designers to create animations that we haven't even thought of yet. So the idea from our design space is to provide these building blocks that would allow designers to create potential animations that transition between data graphics based on the graphic properties, the data, and we provide transition types. These kind of is somewhat our way of codifying or coming up with categories for the commonly used transitions that we saw in our design space, but we felt it was important to provide these building blocks so that an authoring tool could really support designers in creating expressive and new or novel animations.
Okay, that's really helpful. And then Gillian's also asking a question, which is kind of, I'm going to tie in with the question I have as well. So she sees that you can relate these transitions in the design space to transitions that a user makes as they're going through an exploratory process in an interactive visualization system. And of course, as a Viz system designer, when I read the paper, I was thinking, well, this just feels like you could track a design process, the kind of thing we describe in our LitViz work, and the kind of design decisions that designers make in notebooks. So do you think there's scope for moving this approach into other areas that involve, or other processes that involve multiple successive graphics?
So just to clarify, are you talking about the approach that we took for the study or the approach that we took for this framework, the design space?
I'm talking about the design space and the possibilities for moving between graphics that you describe with your, well, I don't know whether to call it a language or not, but the concepts that you have. Because it feels as though you could describe user interactions, you could describe designs, you could describe kind of storytelling approaches that we find. It feels as though there's perhaps scope to build on this to describe a broader set of narratives or even branching narratives that we see in many approaches that use multiple graphics.
Yeah, there is definitely room to grow in that area. And actually, there was a previous year of his paper by McKenna et al. About narrative flow, and especially when it comes to interaction and how users are selecting how they want to navigate through such a data narrative. I think our framework hits on the nuances that come when you add data into animated graphics, and especially for data visualization, where in this type, beyond infographics, there are a lot of objects that are moving in the scene, so hundreds of objects, and how do you create coordinated animations that are meaningful and understandable to the user. But yes, I think a lot of this research is honestly based off of animated graphic design and just how do you move graphical shapes between scenes in a transition. So yeah, I definitely think this could be built upon. Our little niche was focused on the data aspect.
Yeah, and in a way, that's kind of cool to the community there, because Arvin's asking questions as well, where he's wondering, well, would you apply this to a final tool or a prototyping tool? And I'm kind of talking about, well, designing a prototyping tool. So I think it's going to be really interesting to see how broadly some of these concepts apply and whether we need new concepts or the concepts in which they work. So you've certainly given us plenty of food for thought there. Thanks.
Yeah, thank you for the questions.
Okay, let's just scan through, see if we have anything else. YouTube's a bit quiet. Discord looks like we're done. Final call. Anybody typing away? No, in which case I think, John, you can finish off your breakfast now. Thanks very much. Okay, so I think it's probably time for some sketchy linting. And that's what Aspen Hopkins and her colleagues from MIT and Tableau Research are going to be talking about. Hope we can get Aspen on screen.
Thank you so much for having me. My name is Aspen Hopkins, and today I will be discussing VisualInt, sketchy in situ annotations of chart construction errors. I'm going to start with a small activity. The chart you see on the screen before you was presented in a September 2015 congressional hearing. The chart purported to contrast Planned Parenthood abortion rates to their cancer and STI screenings. Does anything look strange to you? As a visualization-savvy audience, you might first point out the lack of y-axis. You might even notice an odd scaling happening between the data points. Why is 327,000, the number of abortions in 2013, higher than 935,573? The number of cancer screenings also documented in 2013. In case it was missed, 327,000 is a smaller value than 935,000. You wouldn't be the first to notice these discrepancies. This was Vox's response to what turned out to be a truly very subtle dual axes. It's quite different, isn't it? Incidences of poorly designed visualizations are common and are only increasing as the internet grows, as tools to make visualizations become more available, and as people attempt to make sense of complex events. We call these mistakes in visual encodings construction errors, when a choice is made in the design of the visualization that either misleads or causes confusion for readers. But actually catching these errors is difficult, requiring 1. Vigilance and attention, high level of data and design literacy, and awareness of evolving best practices. There are some tools that exist to improve visualization authorship, smart defaults in languages like Vega and Vega Lite, or constraints in recommendation systems such as Draco enforce data visualization best practices implicitly. But codified heuristics can fail when authors deviate from expected use cases, and their lack of explanation fails to teach the very best practices they inform. As an alternative, McNutt and Kendallman proposed a linter for visualizations in 2018. Like the equivalent spell check for word processors, linters parse code and surface errors within the code itself. The limited existing work for visualization linting has focused on systems buildings of a linter, relying on comparisons between sets of best practices in code. When disparities occur, errors might be highlighted, but their expression is prescriptive and largely based on code semantics. While building systems to catch errors is important, how we present these errors is also critical. As is well established in design and HCI communities, method of presentation determines 1, the use of a tool, and 2, comprehension of the topic of presentation. Charts are inherently visual, not textual, but the status quo for linters does not hit that mark. Lack of closeness of mapping between the error, one of chart construction, and the chart itself inhibits understanding of said error. Further, when errors are surfaced, their descriptions themselves often require some level of expertise to understand. And these tools are neither focused on experts nor novices, but a middleman. What about readers? A related concern above and beyond analytical correctness is how to build skepticism and encourage critique of visualizations. Why have we focused our tools for catching errors in visualizations to authors when broad data literacy is so low? To focus on not just the errors present, but also how to surface them, we present VisualLint, a design language that can be adopted for the ever-evolving sets of visualization best practices. I'd like to backtrack a little bit. Let's try the same exercise from the beginning with a different chart. What's wrong with this visualization? Imagine if you hadn't been primed to look for errors, or that you had relatively little data literacy. Would you still be able to pick up on the existence of a construction error? Granted, a legend is a very obvious element of a chart, but you'd be surprised by how many people don't catch its absence. What about now? The absence of a legend is immediately clear. We call this method of surfacing visualization errors in situ VisualLint, because lint is visually indicated. Before I go further into VisualLint, let me walk you through our process in both developing its design and evaluating its efficacy as a method of improving visualization error comprehension. We initially collected and categorized visualization rules and errors from a wide variety of sources. We used a simple implementation of these rules to compare Vega and Vega Lite specs against. We then went through an iterative process for distinct motifs for presenting the error expression. Through our evaluative interviews, we developed 4 goals in design and created our final design. Finally, we conducted a 2-part crowdsourced evaluation to explore how well VisualLint presented these errors and also to just uncover preferences in users. Our 4 goals were as follows: salient but unobtrusive. Instances of error expression must be immediately apparent to readers, but they shouldn't interfere with reading the visualization. Direct, rather than listing errors in a secondary view, akin to many code linting tools. User feedback preferred aligning chart elements with error expression. Composable. Unlike spell check, where there's only one reason a word may be underlined, it's spelled incorrectly, there may be a multitude of errors on a single visualization. Thus, our design must offer a composable visual vocabulary for displaying errors. Finally, uncertain. The clean design and inherent rhetorical force of visualizations lend them implicit authority, making it difficult for a layperson to catch errors when they occur. Our design should reflect the fact that best practices in data visualization continues to evolve. Less precise design elements may also help to subvert a visualization's rhetorical force. We found that of our designs, many either impeded reading of a chart, were not obvious enough, were not composable, or did not offer a clear enough reference for the error at hand. In comparison, our final design of VisualInt was displayed in situ, either overlaying or replacing erroneous elements, and could be combined to show multiple errors at once. Its focus on sketchy rendering made it easier to question a chart's authoritative nature and to differentiate between the chart and the lint. We evaluated VisualInt through a two-part crowdsourced study consisting of one, a between-subject study measuring its effectiveness, and a ranking survey measuring preferences for error surfacing. In our prior identification phase, people were shown a chart and asked if it was well constructed or poorly constructed. Upon selecting poorly constructed, we were asked for short or free response explanations. For our between measure, we used 6 types of errors ranging in difficulty, with some being straightforward, i.e. a missing legend, and others more complex, such as the use of negative values with size encoding. We intentionally varied difficulty as it reflects what you readers might see in the wild, and we felt it would warrant greater diversity in response. Our primary quantitative measure in general across this two-sided study was correctness in chart identification errors, which was assessed through dual encodings of these responses. We wanted to know how well people generally recognize errors in visualizations. With that in mind, a major contribution of our between-subject study is a baseline measure of how well people recognize a broad set of errors on their own. After this initial phase, we introduced an intervention consisting of either a text response for the error below the chart with no visual, a visual indication, our VisualInt, or a composite of both text and VisualInt. We then repeated the same measures for the prior phase with new charts to show how effective these explanations for lint were at imparting best practices. Finally, we asked people how they felt about the error expression worked for each error shown. This was our ranking survey. In general, people are terrible at recognizing visualization errors, even when they feel very comfortable with data, even post-intervention. In the prior task, people on average reported 11.2% of errors correctly. Post-intervention, we saw a doubling of correctly reported errors. This varied by specific error, where a missing legend had just under 50% accuracy in reporting. But this is still 50% for a very obvious error. People with text plus text and visual errors had the greatest improvement, followed closely by VisualInt only. But we noticed a surprising and frequent pattern. Groups that were exposed to text-only conditions often perfectly copied its wording when identifying construction errors. While text is informative, it does not indicate the location of the error. Less experienced participants may read but not comprehend or be able to reapply information. This replication of structure may point to a lack of understanding of the holistic meaning of an error. For simple errors, participants preferred VisualInt. Since the legend is missing, the visual is clear as to what the problem is and stands out more than the text. But for more complex errors, participants preferred VisualInt plus text. The text gives context for the visual. The visual itself doesn't give a reason for why it's there. On the other hand, the text by itself is easy to miss. While different methods of error expression may augment this awareness, both in the short term, as seen through the ranking responses, and in the long-term internalization of heuristics, as shown in the post-condition identification task, it cannot replace the deeper engagement that comes from courses, books, and other more verbose materials. Our results show that users need explanations for construction errors, but that this need evolves as they develop expertise and reemphasizes that people lack an intuition for visualizations. VisualInt offers a natural, easily extensible solution to facilitate sanity checks for visualization authors and to generally teach visualization best practices to people. It's applicable for a variety of scenarios, from data journalism to integration with existing tools such as Vega Editor or Observable. We contribute VisualInt, a technique for exposing chart construction errors in situ, and a baseline study for how well people catch chart construction errors generally. Thank you so much. If you have any questions, feel free to reach out to myself or my collaborators, or to read the paper.
Thanks, Aspen. There's applause rippling around the world right now, and some of that's appearing in the chat boxes. So we've got a question from Gillian who asks whether or not what you've discovered here can help address the problem we have with charts and graphics that are misleading, that appear to support particular political or social causes. Do you think there's an application there?
Hello?
I think that was definitely our hope. Wow, seeing the YouTube video and the Zoom is a little confusing. I think in general, one of the major issues that we see right now, especially with COVID-19, is this misinformation can be misinformation via charts and chart construction errors, just like we discussed. And our hope was to find ways to expose and educate a general populace while simultaneously ensuring best practices are continued with authorship. So I think while that is certainly our hope, it would be a little self-aggrandizing to say that is obviously the result that will come up. I think there's a lot of work to be done, but yes.
That's a fair response. Yeah, small steps. I mean, I guess that's where it all gets really challenging when it's about how you deal with the complexity of the error and the discourse around the error. I mean, one of the things I couldn't help thinking was that we had the talk from Ola Rosling last night. And one of your co-authors, Michael, actually pointed to a very kind of considered critique that involved graphics and arguments that he posted online. And classifying that as an error that can somehow be dealt with in this way would seem extremely ambitious to me. So I'm not sure if it's a fair question or not, but is there a way of determining the type of error that your work can really help us with? Is it to do with graphical omission, or can you extend it beyond that? Do you want to say something about the scope to which you think the type of error or the type of guidance that you're working with, the scope that might apply?
Absolutely. I have a couple of responses. The first is, I think our intent with Visualint was to be composable. And so one of the ways that charts and chart errors can be complex is by the introduction of multiple errors or multiple things that seem to bias or influence a reader. And so that composability does lead into deconstructing these complexities. The other thing is, I think that the approach that we've had, especially recently, with visualization linters, like it's a hot topic and people are very excited about it for a reason, because it seems like a solution. But part of the problem is when you're working with designs, there's not necessarily an inherent best thing. It's more of a list of trade-offs. And with that in mind, I think that our hope is for, like, more simplistically to build out this frame of reference and internal comprehension for simple errors, so that people develop more of an internal critique as they are engaging with something that you might see from the New York Times, for example. And so I think the other thing is that it's really simple to add your own list of visualization best practices using this design language that we've developed. But for these really complex interactive visualizations, it's really just a question of, like, can you develop your own sense of data literacy, and can you develop your own sense of design literacy? And so with that in mind, Visualint kind of affords that to an extent, but again, it doesn't detract from this ability to read and write and, like, learn from curriculum.
Yeah, that's nice. I mean, one of the things I like about these sessions with interesting, provocative papers and new ideas is that the people who are online listening are thinking, oh, this might apply to that, and that might apply to this. So there's another question on Discord about uncertainty. Do these kinds of approaches perhaps apply to missing data or uncertain data? Can you see scope for either applying what you know here or doing more work that might help us with that issue?
Right, that's actually an excellent question. So I think that there are two approaches that you could take with uncertainty. The first is this idea of sketchiness. If there is ambiguity in the data, perhaps sketchiness can present that by asking readers to question what they're seeing to an extent, or ensuring that they pay more attention. So from a design perspective, I think that answers that question. But if you're asking about uncertainty from the perspective of, like, can we expose visualizations that have uncertainty, like the data inherently has uncertainty but it's not expressing that, I think that's an additional, like, rule that you could add. Does that answer your question?
Okay, I just lost you at the end there, but thanks. I think that was a nice answer. And as it came in, we have another question, which is from Kevin Han, who says, okay, construction error. How do you know when you've got one? Is there some way in which you can detect that? And can you put people straight? Can you show people what they might want to do to improve things?
Right, so we actually had, in developing our rules of best practice, we went through a series of papers, existing literature, best practices from both psych and visualization journals. And so you can see that in our paper and read a little bit more about our implementation as well. Largely, they were just simple heuristics implemented in JavaScript, and they pulled from a Vega Lite spec and compared against the results. They compared the results that we would get from that spec to what we would expect. It looks like higher level of guidance. So you mentioned something additionally, which was, can you lead people in the right direction? So early on in our development, we actually discussed having automated corrections. And I think that's something to explore later. We include that in the discussion of, you could actually imagine seeing two examples, just like our early in our YouTube video, which showed these two different charts with different axes. And you can imagine a case where there's an automatic, as you hover over it corrects, and then you go back and forth. And so you get this kind of visual comparison that's really interesting. I also think that there are ways to, the interest that we had with looking at visual lint alone as a visual indicator versus the text and then the composite, is that it kind of suggests that there is some verbosity that needs to happen with more complex errors. And so you can imagine a case where, depending on the error, you can add more and more information. And you can also vary that depending on a user. So if the user requires more educational scaffolding, which we also discuss in our discussion section, you can vary that in response.
Okay, thanks. It's really great to get so many authors saying that I'm asking great questions. I'm pretty sure it's just because I'm reading out other people's questions, but this is entirely new for me. But they're nice questions. Keep them coming, folks. That's really good. I think we're out of time for Aspen now. So if I lower my left hand and you raise your right hand, we can do a high five here, I think, probably. You're not going to go for that. I thought you might manage a high five if you raise. Yeah, there we go. That's about right. I think we've got it. Okay, well done. Okay, that's enough of that. Thanks, Aspen. Excellent job. I think it's probably time to think about aggregation choices and their effects. So we've got Francis Wynn and colleagues from Northwestern University and the University of Washington who've done some excellent work, and I look forward to seeing Francis explain it through his video.
Hello, I'm Francis Nguyen, and I'm presenting our paper exploring the effects of aggregation choices on untrained visualization users' generalizations from data. This work was done in collaboration with Jiali Qiao and Jessica Holman, both from Northwestern University, and Jeffrey Hare from the University of Washington. Exploratory visual analytics has become increasingly common in a number of domains through the proposition of tools like Tableau and Power BI. As more and more people who may lack deep background in analysis are using such systems to analyze data, the visualization defaults that system designers build can have a big influence on what users conclude. For example, imagine that Tim, a business analyst in a marketing department, is analyzing some data on which marketing campaign performed best. Let's imagine that he uses a visual analytics tool to generate a visualization like this. What might Tim conclude about the best performing campaign? Now let's imagine that the system Tim used instead defaulted to not aggregating the data, showing him a visualization like the one above. Would his conclusions about the best performing campaign be different? What if he had seen a visualization that combined both raw data and a survey work? Or what if his dataset was much larger than this? Would the best aggregation strategy be different in that case? We know from prior research that how data is summarized can influence how well different tasks, such as identifying a mean or finding outliers, can be performed. However, we know much less about how the inferences a person makes when they're simply examining a visualization to better understand data are affected by aggregation strategies. Today, different visualization systems use different strategies, with some disaggregating the way they feel, while others default to aggregation. And particularly as more and more novice analysts turn to these visual tools for data-driven decision-making, it's important to understand how the nature of a person's inferences and their confidence in those inferences are affected by different aggregation strategies. We thought of two questions related to visual aggregation strategies used to display data. First, how do different aggregation strategies impact the accuracy of an untrained user's inferences, their confidence in those inferences, and the nature of the inferences that they make when looking at a visualization? Secondly, What happens when visualizations are used to examine small samples, as they can often be used in real-world decision settings? How do different aggregation strategies affect generalizations under differing amounts of data? We devised a pair of controlled, pre-registered experiments that target these questions. Both experiments followed the same procedure, but we varied the dataset size between experiments. In Experiment 1, we asked participants to make observations and visualizations that displayed 1,000 records of data, while in Experiment 2, visualizations that only displayed 50 records. The goal was to study how the inferences that novices spontaneously make when looking at visualized data are affected by aggregation strategy, since most studies to date have asked people to do predefined tasks that might not actually capture how they draw conclusions from visualizations in exploratory settings. We designed a study in which study participants, who were novices to visual analysis, look at visualizations of a fictitious online shopping purchase dataset and reported any generalizations they thought they could make about the population from which the data was sampled. We gathered all recorded observations and conducted a pre-registered analysis for accuracy, reported confidence, and the types of generalizations reported. In total, participants viewed 15 visualizations and gave their generalizations on them. For each trial, participants are given a text box to add any generalizations of the visualization they wish to report. They can add multiple generations, and when moving to the next trial, they are asked to report their confidence for each generalization. Participants were not paid more for their generations, so they actually had no incentive to report generalizations or not. To decide on what aggregation strategies to test, we considered various distributional summary charts, such as box plots, multiple types of density plots, and multiple types of summaries, such as sum or mean aggregation. Review of prior work in visualization systems suggested that expressing distributions, scaling to big data, and simplifying inference are criteria that visualization system designers might consider, helping us narrow our chosen representatives. We ended up ruling out approaches that require training to read, such as box plots, and ultimately decided on a disaggregated condition, a mean aggregation condition, expecting visualization users to be more familiar with reasoning about averages, and a disaggregated with mean condition to examine trade-offs between prior conditions. While a mean mark atop disaggregated data might seem like the best because it fulfills all of these criteria, prior work on uncertainty visualization actually suggests that users may overuse summary marks showing a mean to make judgments, such that they ignore distributional information even when it's available. So we considered it an open question whether the disaggregated views with means would actually prove the best for generalization accuracy and other measures. To generate our dataset, recent work from Zagragan et al., which was aimed at investigating the multiple comparisons problem in visual analytics, provides a data generation process that we adapted to allow us to mark a generalization as correct or incorrect. Basically, the idea is to create a ground truth population dataset with known ground truth relationships and patterns, and then sample from that in order to create our dataset in each experiment. By doing this, we can test the accuracy of generalization, as we can mark it as definitively correct or incorrect. In addition to this procedure, we adapted the domain of one of their datasets. We chose one of the two datasets they used, an online shopping dataset, that consisted of 12 attributes of varying data types. To create realistic data type combinations to visualize for stimuli, we formulated 3 data type combinations from the dataset: a univariate view, depicting a single quantitative variable, like income, and 2 multivariate views, a quantitative variable with a nominal variable, and finally 2 quantitative variables encoded in the same view. Additionally, we chose 5 dataset attribute subsets for each data type combination based on what views participants had created in a pilot study that we conducted. We used Voyager 2 to generate stimuli, some of which are shown here. In total, we had 45 stimuli, from which we randomly selected 15 for each participant, 1 for each trial. We launched the experiment on Amazon Mechanical Turk, targeting 90 participants with a high enough approval rating who were novice visualization users. Ultimately, at the end of our experiment, we ended with 1,941 generalizations in Experiment 1 and 1,880 generalizations in Experiment 2. After collecting all of the generalizations, we exclude some based on pre-registered exclusion criteria, such as generalizations drawn from prior personal knowledge. We then code the type of generalization according to Zagragan et al.'s insight classes, which we pre-registered. For more details on each generalization class, we'll refer you to the paper. In addition to Zagragan et al.'s insight classes, we wanted to code if generalizations depicted an effect magnitude. We code a generalization as an effect magnitude if it contains a statement about the magnitude of an observed effect. For example, Midwesterners tend to purchase a lot less than people from other regions, or there is a slight positive correlation between the number of visits and the purchase amount. The open-ended nature of our prompt, the generalizations provided could give information about how participants think about and place confidence in the data. One approach we took to analyze the effect of aggregation strategies was from an accuracy perspective, asking where different strategies led to systematic differences in generalization accuracy. In other words, if a reported generalization accurately reflects a trend in the population. However, to do this, we needed a way to label each generalization as either definitively correct or incorrect. And the first part of this was actually addressing the data generation part of the stimuli. But to actually evaluate the accuracy of a generalization, we needed some additional work. For the generalizations about correlation, we simply compare the generalization to ground truth embedded labels. This is trivial given the data generation method. However, for all of the other generalizations, we had to operationalize the generalization as a query and then test this query against a population dataset generated from the ground truth model. So for example, the generalization, the amount per purchase seems to average around 150. We would query the 10 million record population dataset to see if the population average was approximately 150, with an interval of 10% around this value to account for potential uncertainty. Thus, if a population mean for this value were between 135 and 165, then we would mark this generalization as correct. We follow a very similar testing query procedure for each generalization, and thereby mark each generalization as definitively correct or incorrect. In total, we collected 1,941 generalizations, and after applying exclusion criteria, 1,743. We observed the fewest generalizations in the mean condition, around 30% versus 35%, and the fewest generalizations around univariate data, around 27.6% versus 35 and 37% for disaggregated means of disaggregation. Perhaps unsurprisingly, we observed more mean generalizations when the stimuli depicted a mean mark. We pre-registered hierarchical Bayesian logistic regressions for each of the outcome variables, estimating the effect of aggregation conditions on the probability that a generalization is correct. Our model also estimated FIST effects of order and included random effects for participant and stimuli ID. You can check out the paper and our supplementary materials for full results and analyses. The plot shown has posterior estimates of the effects of aggregation strategy. We see that relative to mean aggregation only, both disaggregation conditions reduce the odds of an accurate generalization slightly, although not reliably, since the 95% intervals on the estimates overlap with 1. We also ran another hierarchical Bayesian regression using the same fixed and random effects but predicting confidence. From the posterior estimates of effects, we see that compared to mean aggregation only, disaggregated without mean marks reduced confidence by a few points. Disaggregated with mean also reduced confidence, but this effect would not be considered significant. We also looked at how likely participants were to mention effect magnitude in the generalization. We noted that disaggregated views were reliably less likely to refer to effect magnitude, but this was weird to us. You would think that with more information about a distribution, a variable would be more sensitive to effect size, not less. And we realized that the way we're coding effect magnitude might be to blame. For example, when a viewer gave a generalization like no noticeable difference of purchases between regions, we would counter that as an effect magnitude because it technically sounds like they're saying an effect size of 0, but we realized that such generalizations were ambiguous. We decided to see what would happen if we interpreted generalizations that mentioned no effect as instead similar to generalizations where they said things like there is a relationship between number of minutes on site and purchase rate. Both types of statements suggest that an effect are dichotomous. They're actually present or absent, but without information on size. A model in the data from this exploratory analysis indicated the opposite of the effect magnitude analysis. People were less likely to refer to relationships in dichotomous terms when they saw any type of disaggregated view. We find that both disaggregation conditions reliably reduce the rate of generalizations with dichotomous effects. Disaggregated views were 0.43 times less likely compared to mean aggregation, and disaggregated with means was 0.57 times less likely. For the purposes of this talk, I'm going to be very brief about our second study where we conducted the same procedure for our second experiment, with the exception where we displayed 50 records instead of 1,000. We wondered, what happens when visualizations instead display small samples? Do the differences we see for confidence, number of generalizations, and types of effects mentioned become larger or smaller? We find that disaggregated views make users on average more sensitive to sample size. On average, people make 3 to 5% fewer generalizations, with 3.6 to 5.9 points lower confidence on average, compared to about 1 to 2% for aggregated. To summarize, our study finds that how you aggregate views can have important implications for the inferences that untrained users make. First, viewing disaggregated views without summary marks reduces users' confidence in their generalizations by 3.6 to 6 points. Viewing disaggregated views without summary marks makes users between 1/5 and 1/2 as likely to produce dichotomous inferences. And finally, disaggregated views make users on average more sensitive to sample size. On average, people made fewer generalizations and also had lower confidence on average. The takeaway from this is that when analysis settings may involve small data sets and users not trained analysis, using disaggregation is a much better option. Or a system like Tableau could use different defaults based on sample size. For example, changing to disaggregated data whenever sample size drops below some threshold. Overall, our work has some implications for how researchers study exploratory data analysis, and we refer you to the paper for a discussion of directions of future work. Thank you for your time.
Great job, thanks. Thanks, Francis. Okay, so just scanning for questions. Lots of applause coming your way, Francis. That's good news.
Good to hear.
So I think one of the things I wondered really was there's this kind of 10% that you throw in halfway through, where you're judging whether or not people are within or beyond, some range of correctness. And it seems to me like you're kind of, I love all this non-binary analysis, but it seems like it's just suddenly throwing all their responses into a right-wrong kind of binary box. And I just wondered how sensitive your results are to that 10%, or whether that 10% is the, I know it's somewhat arbitrary, somewhat established, but are your results sensitive to that 10% that you've decided to use as a measure of whether or not people are right or wrong?
Yeah, so in the previous study by Zagragan et al., they also used a similar threshold, so that's what mainly informed ours. But we wanted to give users a bit more, degrees of freedom to be incorrect, because in their study they're very, they had a much more sensitive measure for that, and that also resulted in a much higher false positive rate in their paper. And so for us, I think we wanted to be a bit more conservative to that. And that's also what might have actually led to our differences in accuracy results, because we found that the accuracy differences between all of the generalization or between the aggregation conditions were very similar. And that was kind of one of the main reasons also of the secondary study.
Okay, thanks. And also, partway through, I'm still just scanning, looking at all the different screens I have here. But I'm going to jump ahead because I don't see anything coming in. So there's this tension I sense between pre-registering. We all know there are good reasons for pre-registering studies, and then realizing when you look at the data that actually that you want to do something different, you want to do something else. And I thought you dealt with that quite nicely here, but I would just love to hear some reflection on the tensions between pre-registration and what happened subsequently. I mean, could you just say something about how you felt about that process having gone through it? In many ways, what you're doing here is a gold standard for the community, but I just wonder what your experience was of discovering that actually you really want to do something else with these data, having looked at it in that way.
Yeah, so I mean, I guess just looking back on the process, I thought that after doing more exploratory analysis of the data after we'd collected it, it became quickly apparent that there was this kind of issue and that there was another experiment that kind of had to be led on. Because originally we had submitted the paper with just the first experiment, and I think doing the exploratory work initially and just recognizing that it is exploratory, a lot of the tension doesn't seem, I guess, as apparent, just because you are recognizing that these elements of the analysis were pre-registered and these elements of the analysis were not pre-registered. And so just by being really transparent about that, I think was the key element in resolving kind of that apparent tension, I guess. And we do mention that the dichotomous thinking analysis and model were exploratory, and we did end up pre-registering them in the second experiment. And so any changes that we did end up making ended up doing the next. We ended up fixing it then in the experiment.
Okay, thanks. And then Michael Currell wonders whether you can get together with Aspen and do some linting to help warn people that data have been aggregated when they're looking at a visual summary.
Yeah, I mean, I think it entirely makes sense. But also I think that kind of what I mentioned near the end of the talk, where kind of changing the type of aggregation default based on the sample size is something that's really useful. Because ultimately, at the end of the day, the paper is kind of about the power of defaults and how defaults ultimately have the most effect on people who are the least experienced. So maybe if we do have a linter for that, that kind of is more in like the end design phase. But in the exploratory part, it could be useful to have some type of warning for when you're aggregating large distributional details or large data sets rather.
Okay, thanks, Francis. Again, scanning through, I don't see any more questions, and so I think let's go for the high five again. I'm quite enjoying these. It's your right hand and my left hand, and we do it like this, and it's all going to work well. And thank you so much. Yeah, we're away. Right, okay. And folks, you'll notice that there's an outbreak, that's probably the wrong word, of interest in Europe in this session. Still a few people waking up in North America. John Stasko has finally added his coordinates to the spreadsheet. So if you'd like to appear on the map at the end of the session, you need to put your coordinates in the spreadsheet, and the URL is right by me. But you shouldn't be doing that. You should be concentrating on this excellent science. And the next piece we have is from Gillian Orisano and colleagues who were looking at large displays and users' intentions. Gillian's got a paper with colleagues from the University of Illinois, and I'll hand over to her.
Hello, my name is Gillian Orisano, and I am a PhD candidate at the University of Illinois at Chicago and in the Electronic Visualization Lab. And in this video, I will be presenting our paper, Many at Once, Capturing Intentions to Create and Use Many Views at Once in Large Display Environments. In the big data era, as data grows in scale and complexity, it becomes increasingly difficult to effectively represent an entire large dataset in a single visual overview. An alternative approach is to enable data analysts to explore a large dataset through the creation of multiple views based on their interests and around their observations. The idea is to enable users to segment their data into meaningful subsets, effectively selecting rows in a tabular dataset, and selecting relevant data attributes, effectively selecting columns in a tabular dataset, and then encoding this data in an appropriate visual template. Multiple views which show different portions of the data from different perspectives can then be presented on a large flexible canvas. Users can arrange and position views to encode conceptual relationships, which has been found to enable sense-making tasks over large volumes of analysis artifacts. In response to these research findings, many systems have been created both for large displays and for virtual canvases that permit users to create and organize many views of their data in support of sense-making and in support of multi-view analysis tasks. While these realized systems have been evaluated, there are still many open questions around how to best support view creation and interaction for visual data analysis in these flexible canvas environments, from interface and interaction design to the use of multimodal interactions. In this paper, rather than study how participants utilized an already realized interface or interaction modality to create views of their data, our goal was to capture intentions to create views in these large environments with flexible canvases, independent of existing interfaces. The idea is that by understanding participant intentions, or what they wish to do, how they wish to create views, we might be able to then design interfaces and interactions around these intentions and accommodate the special affordances of large multi-view environments. So our goal was to empirically examine intentions to create views in a large display environment in a realistic data exploration scenario, while also minimizing the influence of existing view creation interfaces. To do this, we conducted an exploratory observational study in a laboratory setting which featured a large display wall, and we had participants create views of a dataset through a mediator who was located in an adjacent room. The mediator responded to requests from participants by creating views and managing the display on their behalf, and we believe this allowed us to reduce constraints on how participants pose their intentions to create new views of their data. Our setup consisted in a video and audio feed, which allowed the participant to express their intentions verbally and through mid-air gestures to the mediator. The mediator viewed these feeds and responded with one or many static views, which were exported from Tableau, and they presented these views on the large display using a large display software, Sage 2. The mediator also used a chat box and a status bar to communicate with the participant. We recruited 14 participants, 7 men and 7 women, and they explored a local crime dataset, which we believed they would be motivated to investigate. This data consisted in a set of crime instances over several years, containing temporal data such as the day, time, month, and year of the crime, as well as a GPS location and categorical information such as crime type and location categories and neighborhood identifiers for the crimes. To analyze these sessions, a team of coders developed a set of high-level themes from the videos. In order to enable us to integrate together the multiple pieces of information from this study, we created visual scenes that combined the transcript of the request, the screen state before and after a request, participant gestures and gaze, and the views that were created by the mediator. These scenes consisted in 250 visualization requests out of a total of 550 scenes, and we developed codes around these scenes to capture participant behavior. All of this data, the scenes, the transcripts, etc., are available through this GitHub link. The core observation that drove our analysis approach was that in many cases, participants were able to produce interesting states on display that featured many views of their data, specifically many views that showed different portions of the dataset, different subsets, and different data attributes. And these views could be arranged in coherent patterns, groups, grids, clusters, and that this ultimately produced states in the display that could be used for multi-view analysis tasks. Participants arrived at these states in relatively few interactions, relatively efficiently. So this participant did not pose 15 requests to create 15 views, but just a few requests, and she could arrive at this complicated state on the display. So we wanted to understand, in our analysis, how participants arrived at these interesting states so efficiently through their view creation actions. We developed a multi-level coding scheme which captured both how participants requested views and what multi-view tasks they performed using these techniques, and all of this can be found in our paper and supplemental materials. But for the sake of brevity, I'm going to focus in this talk on a few of the interaction approaches that together help participants create many views at once. Specifically, directly asking for many views at once, which we call cast-a-net requests, and copying and pivoting views on the display, which we call referential requests. These actions in particular allowed participants to efficiently create coherent sets of views. First, participants used an interaction style that involved casting a net around an area of interest, in effect, directly asking for many views of their data. Sometimes they would accomplish this by enumerating multiple subsets of the data or multiple data attributes that they wanted to view at once. Sometimes they expressed interest in a region within the information space, such as interest in one crime type or neighborhood, and then they relied on the mediator to fill in a set of views that responded to this expressed interest. We term this casting a net because they effectively cast a net around a set of attributes or a set of subsets of the data, which elicited responses in multiple views. This represented around 30% of direct requests for views. We divided these into several subcategories, which I'm going to briefly mention because they help illustrate how these actions were used in data exploration. First, browsing cast-a-net requests looked at several subsets, several data attributes within one subset of the data, such as when someone is interested in one crime location with respect to several data attributes. Compare Castanet requests instead look at several subsets of the data with respect to a conserved data attribute to compare those subsets. And finally, complex multifaceted requests for several subsets and several data attributes all at once, which could produce a combination of multifaceted representations or a grid of views broken down by their expressed interests. A second major approach that participants used involved referring to existing views as templates that could be copied and pivoted to create new views. We termed these referential requests because they were expressed through reference to existing views. One way that participants would accomplish this is by asking, can I see this? And then they'd point or indicate an on-screen target, and then they'd express some pivot operation to perform on that target. In this case, shown here, there's one view target and one pivot action, and the result is a pair of views with a common data attribute that facilitates a comparison task. Participants were able to scale up these referential actions to produce more than one view at a time. One way that they did this is through what we call one-to-many parallel actions. So participants would indicate one on-screen target, but express multiple parallel actions to perform on that target, producing multiple views, which had conserved features across those views. This, as before, also enabled browsing, comparing, and complex multifaceted tasks over sets of views with common features. In the example shown here, the participant targets a view showing theft and then asks to pivot it to several new crime types to compare the frequencies by a conserved data attribute. Participants also scaled up their actions through collective copy and pivot referential requests. They would do this by indicating many on-screen targets by saying, can I see these views, pointing at a set, but for some new portion of the data set. So they would target many views and express one or many collective actions to perform across all views within the targeted set. The outcome would be a grid of views with conserved features that would enable multiple kinds of multi-view analysis tasks, from browsing, comparing, and complex multifaceted analysis. In this example, the participant duplicated a pair of views from one crime type to another to look at multiple attributes within these two subsets of the data. To return to the initial example that I mentioned at the beginning of this talk, this participant was actually able to arrive at the 15 views on the display in 3 commands, which combined Castanet and referential interactions. So in conclusion, there's some design implications that we could potentially learn from this study. The Castanet and referential requests that I described previously allowed participants to create many views in one action. And by doing so, participants were able to rapidly arrive at multi-view analysis tasks that spanned the display area. The between-view relationships that these actions produced had the capacity to facilitate view layout into conceptual groupings. And this together efficiently utilized the large display area. One possible direction to take in design from this study is to look at how to design interfaces and interactions that would support these multi-view creation actions. I'd like to take a moment to thank my co-authors and the NSF for funding this work, and I'm happy to take questions.
Thanks, Julie. Yeah, we're getting some applause rattling in again. This silent applause isn't quite as good as the real thing. Nice job, though. So we've got a question from Aspen, who's asking about the one-to-many parallel actions, which she likes a lot. But she says, how do the limitations of small screens, when you're dealing with that, compare with the efficacy of working within the large display environments that you've been using?
So typically, in this area, people will use zoomable, infinite flexible canvases that simulate having a really large screen area. We focused specifically on large displays, so it's possible that if you were looking at a small display, you might be less inclined to create so many views at once. But this is not something that we directly target in our study, but would be really interesting for future work.
Thank you. I've got what might be a really dumb question, but that's my job, ask dumb questions. So you have these cast and net requests, and I've issued those in my time. But why does the response to that request require multiple views? Why couldn't you superimpose or juxtapose or difference the views that come back? It almost felt to me when I was reading it as though, okay, people ask for something that isn't that specific in terms of design, and because you've got the space, you chuck loads of designs all over the place. But there is a design decision in there which involves you, I guess, assuming that they really want loads of graphics that are quite a long way apart that they can then make some sense of. So there seems to be some unwritten assumption or design transformation as part of this. So maybe you could comment on that.
So that was part of our protocol. We didn't want them to overly precisely specify. We didn't tell them to specify a view. We said to ask questions. And in some cases, as you say, there was a choice made on the part of the mediator about how to respond to those kinds of questions. It's difficult to respond to a question to look at, say, when crimes occur in a particular neighborhood. When you have multiple different kinds of temporal attributes, you could either make a choice about what they mean by when, or choose to give them multiple representation that broadly address the idea of when or which temporal attribute they might want. In our protocol, we opted to use the display space and respond with multiple views. But in other kinds of setups, like suppose you have a smaller display and you're trying to sort of suggest the best response to that view, you might take a different approach. So that's something that we didn't, it was part of our protocol. We decided to try to use the display space. But participants were broadly happy with the responses that we got in our survey. At the end, they liked it when we gave them multiple views in general. So that was a good sign that it was a good design choice for our protocol.
Yeah, no, I like studies that end up with the users liking it in the end. That's always good for the designer anyway. Yeah, that's nice. So John's asked a question that you can see on YouTube as well, which is about natural language queries, whether those are more convenient for this kind of thing than a more traditional control panel UI.
I think that's a really interesting question. So the participants were interacting using natural language and gesture. We didn't do this as a Wizard of Oz study, so they knew that they were communicating with a human mediator. They weren't speaking to a system. We weren't simulating a system. So we can't necessarily say that if given a natural language interface, they would pose questions in this way. We also don't know if given an interface that was designed visually to reveal these kinds of operations to a participant, whether they would understand or know to use them. I think these are questions that this elicits. So how much is this pertaining to the way they express their questions, like through natural language, through gesture, and how much of this is how people think and want to explore data by asking sort of broad questions or using lots of things on screen to make new things. So I think that's something that should be explored further.
Okay, and that's a nice answer. Thank you. I'm going to open the mic for any final incomings. But it looks like we're probably clear. Yeah. So I thought we had to try a fist bump this time. So hang on, which way around is it? This way. Yeah, here we go. Fist bump down there. That's right. We got it. We're done. I think. Yeah. Thank you. Right. Great. Nice job. And a huge round of applause, please. Oh, thanks. Yeah, I deserve one of those. A punch. Thanks, everyone, for a really nice session. I think we've had a good discussion and good questions, great responses. Oh, we've got another question, but you know what? I'll let you answer that offline. You can answer that one in Discord. There's something else coming in YouTube, and I can't help but take the opportunity, as well as thanking all the presenters and the co-authors. There's huge lists of them, and the folks who are doing the tech here. Man, they've done such a great job. Matt, brilliant job on the tech. All the guys in North Shopping have done such a good job here. Thank you so much. I can't help just mentioning that I'm recruiting, and we have a bicycle club that is going to try and persuade people to ride at the weekend. So if you like bicycles, you can ride a 25, a 50, a 75 or 100k ride at the weekend. Follow the link. It's all documented in the Discord discussion area. We'd love to have people out riding at the weekend if the weather's good. So stay safe, folks. Get on your bikes if you can. Enjoy the rest of the conference. And let's have a final thumbs up and round of applause for our fantastic participants. Cheers, guys. Well done. Thank you.